I'm Pat Brown. I'm the moderator of our webcast today, and I'd like to welcome you to technical webcast number 3 in our CIM and network analysis series. Welcome back to you folks who are joining us again, and just plain welcome to folks that are new. Just a quick look at the series. In our first webinar, Jay Britton and Alan McMorran talked about the basics of power system modeling using the CIM, covering the equipment profile and the diagram layout profile. And then last week, Chuck DeBose walked us through some of the more complex portions of the equipment profile, and he covered areas like transformer, HVDC, short circuit dynamics, and unbalanced models. And today, Lars Ola will talk to us about how the CIM supports power flow cases, and Jay will give us a brief look at some of the current topics that are under discussion in Working Group 13. Recordings of all of the webcasts are available on the UCAI YouTube channel, which can be accessed through the Technical Webinars link on the CIM User Group site quick launch bar on the left. So recordings from the last 2 weeks have already been posted. And a reminder that PDFs of earlier presentations are available at the Oslo meeting site, which is accessible via that previous meeting link on the quick launch bar. One last item before we get started. The CIM User Group has its North American meeting coming up this November. It's the 11th to the 14th of November. That's Tuesday through noon on Friday in Orange County, or LA, California. And as a participant in this webcast, you are entitled to a $50 discount off of the early bird registration, and that early bird registration ends today. If you like what you hear, I would encourage you to attend. There's nothing like being able to talk to the presenters face to face. So with that, let's talk about today. A housekeeping item. All of the attendee lines are muted, and as Kay has been sending out instructions to you guys in the chat, if you want to ask questions, the way to do it is to actually use that questions item on the pull-out window, the GoToMeeting pull-out window on the right of your screen. If you enter them, we'll consolidate them, and I'll present them. I'll ask them to the presenters at the end of our webcast. We will be consolidating all the questions from today's webcast and earlier ones and posting responses to them on the CIM User Group website as well, and we will let folks know where they are. So here's what we have on tap today. Lars Ola Osterlund is going to talk about how the CIM supports the inputs and outputs of power flows. So the steady state hypothesis information that makes up the input, and the topology and state variable information that comprises the outputs. Then Jay will give us a high-level overview of some of the topics currently under discussion in Working Group 13, like changes to the physical network model, which are often referred to as projects. And also he'll briefly introduce the notion of assembling full models from model parts. So with that, Lars, I'll pass it over to you, and if you could just share a little bit about yourself with us first before you get started, that would be great.
Sure.
And there you go. Great, we can see your screen.
Oh, that's fine. Yeah, so I'm Lars Ola Österlund, and I'm working for Ventyx ABB, and I've been doing so for quite a while. I've been in Working Group 13 since 1996, I think. So I've been in this business for quite a while as well. And my major business right now is participating in standards work and work for Ventyx ABB with architecture issues. And I will be talking about IEC 61970-456. So I will actually try to punish you with these numbers a little bit, because it's good to hear them and then finally I think people start to recognize them and remember what they are. I think that's important, so we know what we are talking about. I will also make a little bit of a detour, talk about profiles and profile generation, because that has been and is a big topic, and it could be interesting how that works. I will talk about some use cases behind this 456 specification, the power flow inputs and outputs. I will talk about the canonical models and how the profiles look like when they are derived from the canonical models. A few CIMXML examples, and then I will talk about bus branch node breaker modeling. That's quite a big topic as well, and the boundary modeling. So, CIM profiles, CIM standards. We have I have divided them in different groups with different behavior. The data that is changing slowly is listed at the top there, and I think that other speakers have already talked about them, so I'll skip them over. Then we have the ones that are changing a little bit more rapidly, and that's the topology and the switch statuses. And that is part of the 456, the topology output. We have also in Europe a compilation of the IEC standards that's called CGMS, and the topology profile is for short called TP in the CGMS specifications. Then we have the stuff that's actually changing rapidly. That's the steady state hypothesis. We have all the injections and voltages that's input to power flow there. It's for short SSH in the CGMS. And then we have the final solved power flow state, that is the SV state variables profile. All this stuff is exchanged in a CIMXML format. That is an XML format derived directly from the profile information, and there are rules on how that derivation works. I will not speak that much about this. And CGMS I already talked about, so again, the IEC world has standards 61970 on this, and NCE, they have compiled the IEC standards and made some extensions to it in the CGMS profiles. Steady state hypothesis. When we started with the power flow, we invented the topology and the state variables, and we actually used it for both inputs and outputs. That didn't work very well, because when you use the same information as input and output, the problem is that the state variables show the final result, so the initial conditions kind of disappear. For power flows with the voltage regulation and different regulations in there, that moved the operational point as the power flow tried to compensate for changes in the network. That didn't work very well, so we decided to invent the steady state hypothesis that provide a stable set of inputs that can be reused whenever you want to do the power flow. All those profiles are related. In the center we have the equipment profile, or EQ in CGMS language. Related to that we have the state variables, the topology and the steady state. That's the topic for today, but we also have measurements. That is the input to state estimation, and then we have the schematics. When the intent with the CIM is to have a canonical model that is established as a common agreement on how to model the power system. It's huge. It has a lot of information in there, and it's actually increasing all the time with new additions coming. For instance, a recent one, a fairly big one too, was the dynamics that probably Jacques talked about. So when we have all this massive amount of information, we want to have subsets of this information that describe a particular usage of the CIM. That process is called profiling, and we have a few different ways of doing this, and I would say that this 61970 is probably the simplest, because in that one we just make a selection from the canonical model of the classes and attributes we want in the profile, and then the work is basically done, because the actual messages are then generated according to a description in the 552 specification down there at the left. There are, however, other ways to do profiling as well, and in particular in the XML schema world, there is a little bit of, or has been a bit of manual work on how to actually craft the schemas. This has now been replaced by a set of rules how to do this, but that side of the world includes a lot more steps. And there is currently discussion on harmonization of the ways profiles are being created. So that's basically what you can see in this diagram, the different methods and how they work. Up at the middle we have a green little thing there. That's the canonical model in a file format, and currently we have a tool called Enterprise Architect. It's used to edit and update the canonical model. It's saved as an EAP file, but it can also be saved as XMI. So this information is the basis for creating reports showing the canonical model, and we have CIM Clean. It's a tool developed by ABB that can be used to verify the correctness of the model and find bugs in it. It is also used to actually generate the standards documents for the 61970 series, actually also for the 61968. So these specifications are coming from different working groups. So working group 13 is the place where we develop the 61970. Working group 14 is the place where you do 61968. So we can, with this CIM UML tool, we can derive also statistics and validate the UML model. So it's quite useful. When we have reached a reasonably good quality of the UML model, we are using profiling tools that are used to create the subsets of the CIM model. I won't go into the details down below the profiling tool, but there are many different formats being produced. And we have also a set of different tools for developing profiles. So Enterprise Architect can also be used for the same thing. And then we have a graphical version of the profile with the UML diagrams. There is a little bit of harmonization needed between the tools, because some tools use slightly different data formats, so there is a need to actually improve the interoperability between the different tools. So going back to the topic that I'm supposed to talk about, the state estimation use case. What you can see here is a couple of gray boxes that kind of represent the functions we have in EMS. So we have to the far left a data modeler that produces the equipment model. We have a network model builder that generates the topology. We have a scheduler that creates schedules or records schedules. And then we have the state estimator taking inputs from all these guys here. So you can see the topology and the state variable boxes, they are outputs from the network model builder and the state estimator, and the state estimator also produces the steady state hypothesis. The steady state hypothesis is then used as an input to the power flow. and not only the power flow, because you have many different kinds of power flow applications in the system. You have contingency analysis, you have short circuit calculations, you have lots of things there. So that's the starting point together with the equipment model, and then on the way the results are being produced by network model builder and the power flow calculation itself. The two previous diagrams showed one particular case on how those profiles are used. The world is a little bit more complicated than that, because we have also other producers of data that is used as input to power flows. So in this diagram you can see to the left various different possible sources of input data to the power flow. Then you have the yellow boxes in the middle where you do some processing of the data coming from the left, and the result is the steady state hypothesis output, where we have gathered all the information that's required as an input to the power flow, and then the output is the topology and the state variables. So we have a topology model in the equipment profile that is connecting the power system equipment with each other. The central there is the connectivity node, and the connectivity node links the different conducting equipment to the right together using the terminals. The terminal is just above the connectivity node. When the CIM started, we didn't have good models for describing real-time data with breakers and measurements and stuff like that. So this model was actually invented to support that. So the connectivity node and the terminal is two corner pieces for connecting the breakers or switches and the measurements to the equipment model. So then we have the node breaker style of modeling. So that was the initial usage of the CIM, but we also have planning models and operational planning models. They tend to reduce away switches, breakers and disconnectors. So then we have a bus branch model. The nice thing with the CIM model is that you can combine these two models fairly flexibly, just by including any number of switches and measurements you want to. The model is capable of describing both bus breaker and node. Bus branch and node breaker. So the connectivity nodes, they are then the input to the topology determination, and the topological node thing down there is actually then the result of the topology processing. There is an issue, however, with this. When you do that, the question is, how do you name the topological node, the bus? Because in the bus branch-based environment, you are working directly with the topological node or the buses. So you need a way to maintain the names on the buses. They can't change names every time you do a network reduction with the topology processor. So you have the bus name marker up to the right there that helps us doing that. So by feeding bus name markers into the node breaker model, we could get persistent naming of the produced buses, which is quite important. The topology profile is a selection of what you saw in the previous diagram, and this is what it looks like. So it's a subset, and you can also see to the right there the corresponding DC model. We have fairly recently added HVDC to CIM, and actually also added a detailed node breaker model for the DC part. And the reason for this is we expect DC networks to come in the future. It's not here yet, but it's probably coming not that far away. So we prepared for that. And they are structurally identical. And you may ask, why didn't we use the same terminal that we are using on the AC side? And the reason for this is the UML model is nice when you want to check the validity on data. And it's clearly invalid to mix and match HVDC and AC equipment on the same topological nodes and connectivity nodes. That just doesn't work. So by doing the model this way, to have separate terminals and connectivity nodes for the AC and the DC side, that makes it possible for a validator to discover when you have made illegal connections in your data. So there are two thoughts of school here. A flexible model that's simple and allows any connectivity or any combination of data. Problem with that is you can do mistakes in your data, and you can't use a generic validator to find those mistakes. So by being a little bit more specific in the modeling, you avoid mistakes like this, and you prevent them from happening because the validator will show them to you. So you can, from this statement, understand that I'm a guy that wants to have as specific models as possible to catch the issues in data already in the validation phase. I think that's a benefit of UML, that you can do this. State variables, and state variables represent the power flow result. So what we have here is the injections, we have the flows, we have the voltages, we have tap changer positions and things like this. And this model was created by adding new classes for the statuses. The reason for this is we wanted to separate it from the equipment model. It's very nice from a modeling point of view, but it adds a lot of new objects to your model, and managing objects in software is a little bit of a complication, and it makes it more difficult to handle and implement. So yeah, and now we come to the state variables, how it looks in the profile. So you can see some of the links went away, and we have still the classes and the attributes there, and some of the links that are kind of calculated as a result of the state variables computation. Another important thing with the state variables is the sign conventions. They weren't clearly established when we started this, and some people came out with the generator sign convention, other people came with load sign convention on the power flows, so this screwed up. So now we have standardized that. It's very important, of course. This is the DC part, and what we have here is, let's see now, I think I have a mistake here. Should have the power flows in there. Okay, anyway, it's a set of data for the resulting power flow. The steady state hypothesis. This diagram is complicated because and crowded. You have a lot of classes, and you have a lot of attributes here as well. This is in the contrary to the steady state profile, to the state variables profile, sorry. We added the steady state attributes directly to the existing equipment classes. So this is a completely different approach to the steady state, to state variables, sorry. The benefit of this kind of modeling is that it's a lot easier to describe and handle this data in the software. So I think that was one reason we did it this way. When we create the steady state hypothesis profile, we do it in a CIM tool. within IEC. And this is just a glimpse of that tool, so you can see what it looks like. So you have to the left in this diagram all the different profiles we are managing. And then for steady state hypothesis, you can see to the right exactly which classes are included in that profile. And in this tool, you can click on the different classes and drill down and look at the attributes that's actually included for that particular class. This is the three classes that provide topology input. So we have the AC DC terminal, or the terminal. That guy, if you remember, is connecting the equipment to the connectivity nodes. So you can actually have a lightweight kind of breaker with this connected attribute there. So by manipulating that attribute, we can remove the connection already with the terminal. The other way to do it is to add a switch and instead use the open status on the switch. The equipment itself has a normally in service attribute. It should be shown in this diagram, but it isn't. That actually tells if the equipment as a whole is out of service or in service. So if we look at the SSH and what's actually included in the profile, you can see the classes here and the attributes. I think that's not so interesting, so we continue. This is for the active power and the injection part. And this is for the DC part. So we have the AC DC converter, we have active and reactive power that correspond to the AC injection on the converter, and then we have, depending on the type, if it's a current source or a voltage source, a couple of different attributes for the voltage control and active power flow control. So when we come to the CIMXML data file, we have an example showed here where the topology is resulting in a topological node, and the terminals now connecting the equipment to the topological node instead. So if you remember, we had the starting point for all this is the connectivity nodes, and in a situation where we have the breakers, we make a reduction and take the breakers away, and the result will become a topological node, or a bus as we call them. So we have a new attribute on the terminal then that maintain that linkage. Another thing worth mentioning is the RDF ID and the RDF about. RDF IDs are used to indicate that this object is kind of new, created, and the RDF about indicates that this is a reference to something that's been created somewhere else. There is a discussion now on harmonizing that and use RDF about in all places. So the RDF ID should go away in the future. That's at least what I hope. Same thing for the state variables. We have the topological nodes again. They was created in the topology processing. So now we have are referring to them and telling in what island they appear, because the topological nodes that are connected, they form islands. Typically you should have just a single big island in your network, but if there are some issues, the network may fall apart. And then we have different islands coming. The SV injection is sitting on the topological node, and that's what you can see at the bottom there. We have a reference to a topological node where this injection is related. So a summary on the inputs. We have connectivity nodes, they can be used both to describe buses, then there are no switches, maybe there is a bus coupler, but that's it. Or we can have them between the breakers in a node breaker model. Bus branch topology is described by retained switches. That's typically bus couplers. So if you want to keep the coupler in the model so you can simulate a bus split, then we have the retained switches to be kept in the model. We have the equipment normally in service where we can actually take equipment in and out, the complete thing. And we have the AC/DC terminal connected that tells if the equipment is disconnected on one particular side. So there are actually two different ways of doing this. If you want to disconnect something completely, you can, for a line for instance, use the AC/DC terminal, open the AC/DC terminal in both ends of the line, or you can use the normally in service and take it out that way. Node breaker topology is the same thing with the equipment in service and the connected flag, but you also have the switch open. So there is a topology processor will have to look at all these three attributes to actually determine if something is in operation or not. And the result of all this processing will then produce the topological nodes. And at the topological nodes you will have the injections and the voltages, and the power flows will be at the terminals, as indicated in this diagram here. So we have some interesting use cases with the retained switch that is kept in the model. You can simulate bus splits easily, but you cannot do line transfer easily. Then you need actually to do model change in the bus branch world. So you need to take the model and actually change it so that the transferred line is now moved from one of the buses to the other. As I said before, you can use the AC/DC terminal connected attribute to tell that a line is open-ended. And a long transmission line that's open-ended will still be energized from the other side. So to calculate the voltages at the end of the line, we need a topological node where we can put the SV voltage and injection on that line end. So when we look at the network model, we have different parts in the model coming from different responsible organizations. For instance, a TSO will be responsible for its own network, while the neighboring TSOs will be responsible for their kind of external network seen from the first TSO. So this means that a network model is partitioned into pieces with different authorities, or model authorities as we say in the CIM world. If we have two areas maintained by different organizations, they still have a common connection point at the tie lines. And the way we model this in the CIM is to specify boundaries. So the boundary then is typically the line, if we talk about the tie line. Within the line we have the connectivity node, that is the common point of coupling, so to say, between the two organizations. And then we have AC line segment in the two networks connecting to the boundary. And the terminals at the AC line segments in the network will then point into the boundary. So in the CIM, you know that the AC line segment should be part of a line. So the AC line segment needs a reference to the common line in the boundary. And the terminal at the AC line segment need to have a reference to the connectivity node in the boundary. This thinking is now worked on fairly extensively, and I guess that Jay will continue to say more about it in his coming talk. because if we want to automate the exchange of models and have this being done automatically, it's important to be able to exchange metadata describing what regions you have in your network and what versions of the model you have in the regions. So the CIM model will be extended with information for that pretty soon. Working Group 13 and also N3 is working on this right now. So the boundaries and the network models will be further developed. If we look at the boundary particularly and the connectivity node in this diagram, we have processes in the TSOs where you actually cut your network at the boundary. If you do that, there will be a power flow into the cut AC line segment that you need to take care of. And the way it's done right now is to add an equivalent injection then, connecting to the connectivity node within the boundary. This slide is a very similar situation with the difference that instead of a transmission line or a tie line being the boundary, a substation itself is a boundary. So at one point in the substation we will have a connectivity node that's defined in such a way that it's known by both connecting parties. This makes it possible for the two parties to actually link with the boundary. So we have the substation and the voltage level and the connectivity node as the boundary objects in this example. And then again we have an equivalent injection for supporting of cases where you actually cut away one of the sides. So I will say a few more words about this cutting on boundaries. So this diagram try to illustrate the day-ahead congestion forecast process in MSOE for the TSOs. So what happens here is that the TSOs, they get schedule values for the production and the system load as well as the tie line flows or other exchanges between the different regions. So the TSO then take those schedules. A schedule is a time series data, so you have typically 24 hours, values for 24 hours. So what you want to do in the congestion forecast, you would like to make sure that the power flow gives a feasible result for each hour in that time series. So what you do, you map down the time series on your network model and your boundaries. So the equivalent injection come into play here. So the tie exchanges, they end up on the equivalent injections and the productions on the generating units and the load forecast on the loads. And then you can do the power flow for your own region. So that's what's happening in Europe on the NSOE TSO level. So then each TSO, they do the power flow for the schedule hours. When that's done, you need to look at all the TSOs taken together. So what you actually do there is you take the network models from each TSO, the network model that they used for their day-ahead congestion forecast hour, and then they also take the power flow results. And no, sorry, you take the injections between each TSO's power flow and you merge them together, so you get the complete network with including all the TSO, and then you solve the power flow for the whole thing, and the result of it then become a topology and state variable solution for the complete network. And then you can verify that that the situation is feasible for the schedules also for a larger region. And recently in Europe there has been created special organizations for this called security coordinators. So they collect all the power flow solutions and the network models from the member TSOs, and then they do the power flow and congestion forecast for the whole larger region. And when we did the 456 specification in IEC, we actually developed this support for this merging, model merging, and the handling of the schedules. So that's part of this 456 specification and also in the CIMS. Okay, I'm done. I probably did it a little bit too fast, I think.
I don't think so. That was great.
Okay.
Very good.
So maybe I don't know if you gathered some questions, Pat, for this session.
There are. So let's address them right now, and then we'll transfer it over to Jay after we get through these questions. So the first one is are network reduction tools available in CIM? If they are, can you please point out where to get them?
Yeah, network reduction tools, that's a software that helps you reducing a mesh network into a simplified injection and some equivalent branches. So the tooling stuff isn't incorporated in the CIM, but there is models for it in CIM. So we have a little package called equivalent, I think, where we actually do have support for the resulting reduced equivalence. But equivalence is a fairly tricky issue. You have people look at it very differently, and you may have equivalents that are created manually, or you may have equivalents that's derived. And the manual equivalent, you may want to have, for instance, a generating unit representing a couple of smaller units. That's still a generating unit, so you want to keep it as such. So then we have a flag on generating unit, I don't remember the name now, that allows you to do that. Aggregate unit, I think the flag called, or aggregate. But you saw in my presentation here, let me just move back a little bit. So equivalent injection, that guy I think is from the equivalent package. So so there is a model in CIM that supported the result of a network reduction. Over to you, Pat.
Okay, I'm betting Jay would like to weigh in on this question too, about equivalence.
Yeah, it's a favorite subject, but to keep it short, I think the other thing that's important to say about equivalence is that the decomposition of overall cases into parts using these boundary specifications enables you to generate equivalents that fit into the structure using the standard boundaries, and that makes management of cases with equivalence much better. But as Lars-Ola said, the actual equivalent calculation is not standardized by CIM. It's only the input and output that is.
Yeah,
Great.
and that there are so many different opinions on equivalence, and the equivalent that Jay is talking about is a standardized, simple load type of equivalent that is automatically fitted to the boundary. And actually what you can see in the picture here, equivalent injection, is that kind of equivalent, but not all people are happy with that simplistic equivalent, and then they want a more advanced thing with some kind of a generation unit there with lots of capabilities to react to changes in the grid. So this is a complicated topic.
So another question, what's the difference between writing RDF about and RDF resource?
Yeah, I kind of regret I brought that up. As I finalized the discussion was that they are actually they should be the same in my opinion, and in working group 13 I'm working for removing the RDF ID and just having RDF abouts all over the place, because in the 552 specifications there are added some semantics to the RDF ID that in my opinion is not necessary and just complicate things. So the simple answer is that they should be the same. There are some rules saying that, as I said, an object that is new, kind of start its lifetime, should have an RDF ID to indicate this, and then references to existing stuff should use an RDF about. But that rule is, in my opinion, adding more complication than it adds resolve issue. It adds issues rather than removing issues, in my opinion. Back to you, Pat. So, Pat, are you there?
There is yes. There's a danger to going on mute to try to make our end of the world a little quieter. Sorry.
Yeah, it is.
Okay, so the next question comes from Carl Froughton, and it is, how would a contingency that involves a boundary connectivity node be dealt with?
Well, I don't think that's an issue.
Yeah, there's no problem with that. Once you combine the models, it looks just like a model, and you can have contingencies anywhere, including on boundaries.
Yeah, and boundaries are well defined. I mean, they are actually more well defined than any other pieces of the models, because a boundary is an agreement between two parties. So that agreement is makes the boundary kind of documented and managed in a much more stable way than the rest of the network. Because if you change the boundary, you need to make sure that everyone that uses the boundary follows you. So I think that what will happen in practice is that the boundaries will be defined, and then they will be very stable, and changes to them will only happen when you actually add new tie lines, for instance, or add a new feeder in a substation that goes away to some external party.
All right, we have a leading question from Stefan. Who maintains the standard profiles, diagram layout, topology, SSH? Are the standard profiles synced every time a new CIM UML is released?
Yeah, it is actually. So the way Working Group 13 actually works is to develop the CIM model. So let's say that we have now CIM 16 being published very soon. Then the 61970-301 document describes the whole thing. That's the canonical UML. So when that work is done, we walk through all the profiles and update them so they are in sync with the basic CIM model. I haven't showed in my presentation today how this works, but there is actually documentation and descriptions how to do this in the IC specifications, and there are juries on the versioning of the profiles so that you can identify the version of the profile easily. And in the CIMXML data exchange format, the version of the profiles of the data that's included in a message is also described. So you can link back to the profile that was used to actually produce a particular message with CIM data.
You might add the comment that the reason that the Working Group 13 profiles are synced is because they're used together. And so they need to be synced, but that's not in general true about CIM profiles.
Yeah, I'm too narrow in my description here, but we are talking about power flows today.
Right. Right.
And I think that's that's where our domain is currently. But if you look at the, I mean, between the different working groups, then the situation becomes quite complicated. So if 13 updates the canonical model in 13, then both 14 on the IP processes and distribution side, as well as the energy market side, they will have to sync their UMLs with this base UML, and then they will have to update their profiles. And the three working groups are working in parallel, so the syncing of these working groups is it's a little bit more complicated, and it's definitely not synced between the working groups. So for instance, if we take the geographical location profile that probably will be located in 61968, that profile will probably live its own life with its own evolution. So ultimately IC or TC57 may end up with the compatibility matrix showing which version fits with which other profile version, but we aren't there yet.
So one more question back to the network modeling end of the world. How do you coordinate voltage conflicts at a boundary where you have different model authorities for a complete power flow solution for the entire network?
Yeah, we have the voltage level in CIM, the voltage level class, and one way to do it is to standardize the voltage levels and put. We have been talking about this quite a number of times. There are some basic data that preferably should be standardized across all power network, on the whole power network. So that's one way to deal with it. And then we will also need a separate profile for standard data. For instance, voltages. There are some other things as well that could go into this profile. So that's one way to deal with it. The other way to deal with it is to allow for different voltages to some extent. And I think in the profile we say that variation of 5 to 10% is allowed. And as long as you know the voltages used on both sides, when you do the per unit calculation later on, you will get it right in the end anyway.
All right, so perfect. And that is the end of the questions that have come in thus far. So Jay, let's shift over to you. And I am making you presenter now. And if you want to share your screen, that would be great. Good. And also just a few words about yourself, if you would.
Okay, my screen is showing?
Yes, indeed.
Okay, good. Yeah, I'm Jay Britton. I'm currently an independent consultant. My work history, though, goes back quite a ways and includes work at utilities, probably more at vendors than anything else, but also quite a few years of consulting experience. Most recently, I was with Alstom in the EMS area, and my main area of work has always been network analysis. And like Lars Ola, I've been around the CIM standards for a long time. So with that, I think I'll move into this concluding portion of the webcasts, and this is on model parts and assembly. And I think Pat said this is current work that is in progress, and that's true, although most of what I'm going to show you today here is things that you can do today. What The active work in progress is more around formalizing and making more convenient things like exchanging of stored procedures and other things like that. So I'll try to clarify what is and what is not current. So first we're going to go to this slide that you've seen before if you were watching the first webcast, and I think Larzola also showed it. This is the reference diagram for network analysis cases from Working Group 13. And I'm not going to go through this whole slide again, but I want you to take a look at the upper left part where we have model parts and projects labeled. Because what I'm going to focus on here is the idea that you can create model parts, and many of these model parts can be created and reused in many different ways, and they're valuable source, sort of master information for creating cases. And when you create cases all from the master information, then all of those cases are consistent in terms of the way they represent the power system, which is going to enhance the quality of all of the network analysis that's done. So the model parts and projects consists of two main aspects. The network as built model parts. So just to give an example, if you are a transmission system owner, you would probably be the party responsible for creating a model of your transmission area, but you're not the party responsible for creating models of somebody else's transmission area. So you're creating a model part, the part that represents your system, but you're creating a complete description of your model, your transmission system as it is currently built. And we referred to those sometimes as full model parts, just meaning that you created a complete description of your transmission territory. Now, to complement that and to make the model cover all points in time, especially future points in time, we have another section called here the planned construction projects, sometimes just shortened to projects. And there's a little diamond or triangle symbol there. Those indicate that projects are defined in terms of changes to the as-built model parts. So they're incremental specifications. They say that in this construction plan, what we are going to do is remove this, we're going to add this, we're going to add this, we're going to add this, and there will also be a time associated with that and other annotation that will tell you what that project was about. And when you have an as-built model part and a collection of projects forward into the future, you've essentially established a timeline so that you can create a view of the network at any future point in time. Past point in times are also important. Those are usually managed as older versions of complete as-built model parts. So you wind up with a complete past, present, and future view of the network. The other aspect of model parts that's really important is something that's illustrated on this slide, and you start in the middle in this thing called a unified grid model. What I've sort of illustrated here is a grid that's divided among various transmission authorities A through X, And those are the transmission owners that make up this grid. And so in terms of supplying the definition of the grid as a whole, each one of the TSOs, A through X over on the left-hand side, is responsible for creating the model part that represents its own territory in the unified grid model. Now, Larzola talked a bit about boundaries. So when you have, let's say, A to B here, you have a boundary between A and B, and there's a formal CIM process for defining the boundary specification. Those boundary specifications allow someone who creates part A to use the AB boundary and the AE boundary to check whether their part fits properly into the whole structure. In other words, you don't actually need all of the other B through X models in order to make that check. You can just do it against the boundary specifications that are relevant to A. So we also know over on the right that there are many studies of different kinds that are run on this grid. And some of them are interconnection bulk power planning studies that take sort of high-level views of the whole part. Others have more depth in local areas. In general, what we have is that studies don't have the same extent. The goal with CIM is to be able to reuse the model parts for all the kinds of studies just by selecting the model parts of interest. And most of the rest of my talk is going to focus on this process of defining model parts and then using them to create different kinds of studies. Definition of a model part. Now this is a definition that is a bit still in the works, but the principle here is supported currently in the CIM. A model part is a set of CIM data that can be composed with other model parts to create a complete model. And then it says there can be any number of instances of a given model part that are usually referred to as versions. This is usually used to just track as-builts. As new construction completes, you create a new version of the as-built. And a model part has a model part specification, and this basically describes the information about what the model part is for. A framework it's basically the grid that I just showed you in that unified grid model, but what we're working toward in CIM is a formal way to describe the framework. And there are two main kinds of framework parts, frames and boundaries. I'm just going to illustrate this with a diagram here. This shows a framework with three regions, each separated by a boundary. And let's look at frame A, for example. Why is it that I don't call this model part A? Well, the reason is that the frame is more or less defined by the boundaries, and then there could be multiple versions of model parts that fit into that same frame. For example, if you're France, of course, and this frame represented France, you would have made a model part for you. But nothing actually prevents Germany over here from making its own version of a model part for France and fitting it into the French frame. And we have found in doing use case analysis of this, that it's important to separate the frame concept from the model part concept, even though they're very closely related, because a model part is designed to fit in the frame. Further with some examples. Here's another grid, and it shows 9 TSO frame parts and 12 boundary parts. Now, I'm just going to take a minute here to point out that every time I use boundaries, they are bilateral boundaries. That is, they are boundaries between two frames. You can lump all of the boundary stuff together and stuff that you don't really have to do it as bilaterals. Bilaterals turn out to be the most efficient form, because when you get a little bit further down and we start talking about assemblies, you won't want to use all the boundary conditions in every assembly. And when you have things in bilateral pieces, it's always just a matter of picking the parts that you want. So we work in bilateral boundaries. Now, I'm going to go on a little bit. So far I've just showed you things that have to do with territorial divisions, more or less geographic or TSO ownership or something like that, divisions. But in order to really make our many cases from common parts work, we also need to be able to go down and look at partitioning of models based on it's going to be primarily a voltage level basis. It's really the electrical importance of the parts of the grid in terms of whether they are locally important or broadly important. And this slide illustrates one TSO that is decomposed into a bulk power part, which is the part, for example, that would be of interest in any kind of interconnection-wide study case. And then it could have various local, what's labeled here as subtransmission grid parts. And those subtransmission parts can be separated by boundaries from the bulk power, and they can be separated from each other by boundaries if that's necessary. And you can have injections and consumptions. That's what this INJSCON, in other words, load and generation. You can have load and generation directly attached to the bulk power, although if you have a load associated with bulk power, that would be a major industrial load. The more normal kind of load actually comes because you have this boundary to a sub-transmission, and then there is more detailed load and injection data on the sub-transmission part. And if you want to reduce away the sub-transmission, you reflect the load up to the boundary. I'll talk a little more about that later. You can keep going with this decomposition, and you can just keep going as far as you want. You could go all the way down and represent distribution feeders and on down, and you could get even into consumer premises by continuously sort of or recursively decomposing parts of the structure. I don't think initially it would go very far, but I think in the long run this has quite a bit of potential value, especially as we get more and more important parts of the grid located in the distribution. Okay, so I'm going to shift now to talk a little bit about assemblies. An assembly procedure describes how to assemble a model. A manifest describes a collection of parts. I'm going to have to speed up a little bit here. let's say North is putting together a study, and it's not a broad interconnection study, but he does need some representation of his neighbors. So he's decided, and this is step one in conceiving a study, what TSO frames must be included. Well, he says, I'm North, I need North. I also need some representation of Northwest, West, Central, and Northeast. That means he has to pull in the boundaries that connect those pieces together. Plus, you'll notice down here, there's a boundary. There's 4 boundaries here that are sort of one-sided. For example, Central has an east-central boundary, but no east on the other side of it. Other bilateral boundaries are complete because they have representations on both sides. To complete the case, for each one of the boundaries that only has one side, you need to develop what's called an edge model. And the simplest form of an edge model, and this goes back to the question on equivalence that Larzola was answering, the simplest way to create an edge model is just an equivalent generator stuck onto the tie lines. And you can, for that kind of an equivalent, you can automate the process completely. The other question that the North study engenders is how much detail of each one of the TSO frames. So this is how far to go down into the decomposition. So this suggests in this drawing that North has included his, I switched over and renamed it as mid-grid here, but it's included lower voltage detail for North because this is a North-focused study. On the West, though, and probably with all of the other ones, you would do it similarly. Only the bulk power grid was grabbed, and there was a boundary there and an edge model created to represent the loads in the lower process. Now, there are various ways that you could calculate the loads in those edge models. The best ones are where West has some case solutions, and you can actually get the tie flows at the or they're not tie lines, but the flows at these boundaries, and use them to create the edge models. So, an assembly procedure selects the model parts, makes the necessary updates to model parts, for example, to go forward in time, sets up a steady state hypothesis, executes topology and power flow to produce a base case, validates as necessary, and then export to your favorite set of planning study tools where you run as many different variations on that original base case as you need to do. There's an example here which I think I'm not going to go into because I think it's better to have a little more time for studying or sorry, for taking questions. But I just want to point it out, and it's in the PowerPoint, and you could take a look through it. This takes a particular kind of case. This is a day-ahead congestion forecast, which is one of the NSOE type cases, and it provides a little bit more of a detailed step-by-step outline of a case assembly, and walks through the selection process more or less that I just illustrated, except that it adds a little more detail about how projects come into play, and you can see it's about well, it's about 16 steps long. So I think I'll stop there and take questions, Pat.
All right, very good. So we do have some questions, and you probably will want to back up a bit, I'm imagining, Jay, to refer to your slides. The question was, in the example, why was west needed if east was not? Since west doesn't have a direct boundary with north either.
Well, it's not, I mean, the most obvious thing in most cases is anybody you're directly tied to, you're going to need to model. But let's see, where did we do that? Here. What could be the case is, suppose you had a 765 loop that went north, northwest, west, central, and back to north. You would want to model west, even though you don't have a direct connection with west, because there's a significant flow-through path that goes through west. And if you're running a lot of kind of studies, especially if you want to do contingencies in the external area that are important to north, an outage over here, the 765 is important. It's that kind of consideration. And I just arbitrarily said here that west might have one of those and east didn't.
Very good. Next question. Are the boundary connectivity nodes in Jay's presentation the same as those in Lars?
Well, yes. Although, let's in this slide, if I explain this a little more carefully, these circles here represent nodes in a graph, and you've got lines. Okay, now these nodes are not necessarily any specific kind of power system object. They're just objects, and these lines here are relationships. And you can make up boundaries in many different ways, and there are different reasons why one interconnection might want to form boundaries in one way and another interconnection might want to form them a little differently. But usually it winds up that an object that's in the most fundamental objects in power system boundaries are connectivity nodes, and that's what Larzola is illustrated, and that's also what my premise is.
Yeah, I would say so, because I mean, you can make diagrams on a more conceptual level, and that's fine. But if you are going to the bare bone detailed model, then you will have a connectivity node there. That's absolutely clear.
Yeah, but that's only because we've designed connectivity nodes to make sense as boundaries. We've tried to make them lightweight, so they don't have much data. They wouldn't change very often. They would only change if you built a new tie line or something like that. So, and one objective in creating boundaries is to make them as stable as possible and as simple as possible.
Another comment on the boundaries, you will have the lines and the substations as well in the boundaries, because you need to agree on the name of the substation you have there in the boundary. So the container objects will also be in the boundary, including the connectivity node.
Yeah. But,
okay,
yeah.
Another.
So go ahead, Ben.
All right, will do. Another question regarding model and frame. Is it essential to have a prototype model of other parts of the network into which you don't have detailed visibility, or is it sufficient to have an equivalent injection?
Let's see. Okay, so if I get the sense of this, let's say A and B are getting together and they're all ready to go and they want to exchange detailed models, but C is not playing in the game. And so A and B are sort of left to figure out what to do to C. Yes, it's very reasonable for for A and B to define the boundary between themselves, begin exchanging their detailed model parts, and they can sort of act as proxies for C. They can create a boundary, and they can create whatever kind of model is good for what they're doing, as simple or as complicated as it's needed, but it's not actually coming from C because C's not playing yet. And that's actually an essential stage in getting this kind of an idea into practical implementation, because it's very difficult to get everybody to sort of go at once. And the fact that you can piecemeal the adoption of this kind of framework idea is pretty important as a transition strategy.
Yeah, I would like to make a comment as well here. This diagram you're showing, Jay, it has a frame C, for instance, there, and we have this little cloud thing that has a lot of objects at a fairly detailed level. We can assume that this is the fully detailed version of the model part for frame C. But we could also envision a case where someone took a network reduction program, fed the model part, showed in frame C into the model reduction, and out comes another much smaller model that will fit also with the boundaries. So then we suddenly have two different model parts that fits in the same frame, in frame C in this case. So that's one case where we have multiple model parts fitting the same frame. Then we can also assume a situation where we have the time in play. So at the current time we may have the full model as it looks in frame C right now. But let's say 1 year ahead we have made some fairly large changes to the model part for frame C. Then we have a model part 1 year ahead with a slightly different model. So the frame thing is kind of a definition of what the model parts are supposed to appear for that frame. So in my opinion, the frame concept is very nice because it allows you to have and identify multiple model parts that will fit with this frame for many different reasons. For instance, the power system projects in time and the network model reductions currently.
Yep, I agree.
Very good. All right. Which part or subpart of the IEC standards contains these new concepts? Are there plans to represent them in upcoming UML releases?
Okay, good question. Very good question, because this goes to the heart of what's what is and what isn't current. This partitioning in the current specification of 452. 61970-452, you will find the concept of a model authority set. Now, in this framework drawing, there are 6 model authority sets. The 3, actually it's the model parts here for the 3 frames, and I didn't mention, but when you actually populate a boundary, that's also populated by a model part, and you can have multiple model parts that define boundaries. This would especially happen whereas Larzola was pointing out, you go forward in time and some new tie line gets built. So the partitioning into model parts is covered in the existing standard. But you won't actually find a UML class called model authority set, because the way you actually do it is just by the fact that you can select objects to include in a given exchange, a 452 exchange, and those model parts can have references outside it's outside itself. That is a reference across from one object to a boundary, for example. So all of the standard that is needed to send a model part from one party to another exists. What does not exist is a way to describe in CIM and exchange a description of the framework, and a way to describe the fact that a given model part fits into a certain position in the frame. And we're hard at work right now creating that, because we think it's a much better idea to have that standardized than to allow sort of people to make up in their own business processes ways to use the existing model authority set concept to do this. I hope that made sense.
All right, there is a question related to outages and projects, and what the distinction is between them. So, for example, if a future outage, say it, and I'm having a little trouble with the question, say an upgrading to an AC line, is that defined as a project or an outage? Or what's the difference between the two? Let's put it that way.
A project here is an increment on the EQ, the equipment models, which is the physical construction of the system. So if you're building a new line, that requires an incremental EQ description. That is a 452 type description. You have to describe the characteristics of that new line. If you're doing an outage is taken to mean a change in the status of the line to remove it for maintenance work, for example. So the open-closed status of devices in the network is part of the steady-state hypothesis, because you can change the status of components as an operating choice. Right.
Jay, may I comment the word outage? Outage has two flavors to it that could be quite confusing. We have the planned outages that we are talking about here, and then we have outages and faults, that spontaneous events happen in the power system, and we are not talking about faults here.
Right. Good point. But the similarity between these two things is that they are incremental specifications. That is, they're specifications of changes. The difference is that projects apply to EQ, outages apply to SSH.
Excellent. Okay, there are more questions coming in than we're going to be able to address, but there was one that I thought might be good just to briefly touch on, having to do with any standard definition with respect to how deep in terms of voltage level that modeling should go. I just thought that might be kind of a good launching pad for the no, but it sure could be used down into distribution.
Yeah, I think it's going to be a little bit unusual for a while to see a great deal of depth. The illustration that I gave of transmission and subtransmission, that one's pretty commonplace, and I would recommend it right now for anybody that was adopting these kinds of procedures. You should probably think about the model of yourself as others need to see it in a bulk power representation versus the model of the other parts of your own territory that you need to see that others don't. But that's mostly a transmission-oriented description. I think the connection to the distribution will happen more on an as-needed basis, and it'll be driven more driven by things like the importance of wind and solar and DR activity down in the distribution. It'll be driven by the availability of and the interest at the distribution level in doing analytical studies like, say, volt-var optimization on feeders. If you, for example, just to take one example, if you had a utility that was really interested in a volt-var optimization program, they will need to create network quality models of the distribution to support that, and they'll need models of the substations. And why not share that model of the substations with the transmission guys rather than rebuild your own model of the substation? And that's kind of a logical point at which you might merge or want, sorry, not quite merge, but want to connect the transmission to distribution modeling. And I think if we look down the road 10 to 15 years or something, there'll be a, you know, this will get more and more commonplace as we get more and more into the smart grid type solutions.
Great. Thanks, Jay. And with that, we're going to conclude the webcast. Thanks to all of you for attending. We really appreciate it. It's wonderful to see this much interest in CIM for network modeling.